What's going on, everybody? This is going to be Mr. Diamond working out this problem that we got right here. You'll notice I gave you two of these to do yesterday, but this is a whole extra problem that I had on the 7.5 worksheet that I cut off because I don't want to stress you guys out too much, so I made it only 4 questions instead of 5. But we're going to work out all of these problems. So if you are interested and you didn't do the practice problems yesterday and you want to just see how well you're doing or you want extra practice, I would recommend maybe trying some of these by yourself without actually watching this video first. Although, if you're watching this because you want help, I would probably maybe watch the first couple of questions and then do the last couple to see if you can get those after watching another example problem. So we're going to switch over to hand cam. But just to make sure we understand what our equation is going to be. It's going to be for the reaction manganese 3 oxide decomposes. And remember, decomposing is when something breaks down. It's going to turn into its components. So we're going to switch over here. And we're going to get my balanced reaction or balanced equation. So balanced equation. And in this case, it is manganese. Manganese is Mn, and it's oxide. So oxygen is O. So that's manganese and oxygen. And then it says it's manganese 3. Now that Roman numeral 3 could mean you put a 3 down here, but it does not. Remember, that is not what those numbers are for. Some of you might think that it's, okay, that's how many manganese I have, but no. It is the charge of manganese, and then the charge of oxygen is 2+. So we're going to cross our charges, and we're going to get Mn2O3. And then it said it's decomposing. So decomposing means we're just going to draw an arrow. This is the only thing on the left side. And if it's a decomposition problem, remember thinking back to our types of chemical equations questions. Manganese and oxygen, that's only 2 pieces. The only thing that 2 things can do to break apart is to turn into their individual components. So manganese would just be Mn. And then we could just put O, except oxygen is special. Remember, it's on that list of 7 diatomics. Yes, you do have to keep those in mind as well. I told you that there's a whole lot that's going to be building you need to know. Because oxygen would be alone here, it's going to be O2. Now we have to balance it. We've got 2 O's and 3 O's, which means we'll have to do this. And that means we've got a total of 4 manganeses on the right side. So our problem here is telling us that if you take 2 Mn2O3s, you can break those down into 4 Mn's and 3 O2s. And just to make sure, I've mentioned it a couple times, but I had some emails about this. You don't have to convert only between things on one side of the equation. All of this is up for grabs. This is all a ratio. 2 Mn2O3s would give you 4 manganeses. 4 manganeses should have meant you also got 3 oxygens. So these all can be exchanged between each other. Now, something that some of you might have realized is useful to do on these problems, but you don't always want to do, because if there's a whole lot of questions, it can just kind of waste your time. Or if there's not a whole lot of questions, it might be a waste of your time. But let's just go ahead and get all of our formula weights / molar masses, just so we don't have to go back and look them up later. It'll save us a little bit of time here. So oxygen, O2, remember we do have to count the fact that it's O2. O2 is going to be 32.00, and that's just 2 times 16.00. And then manganese is going to equal 54.94. And these are all grams per mole numbers. So to get manganese 3 oxide, our Mn2O3, I'm going to have to take this, multiply it by 2, plus 32 plus an extra 16 would be 48. So that'll give you a mass for Mn2O3 of 157.88, and that's also grams per mole. Okay, we now have all the information that we're pretty much going to need for all of these questions. It's just going to be what order we apply them in and whether we use the pieces that we have or not. So I'm going to click back just so we can look at the question again. So the first question we have is find the number of moles of manganese. So manganese is our goal product here, and it's moles of manganese produced when 56.23 grams of manganese 3 oxide decomposes. Okay, so we'll switch back to our hand cam. So our number that we're given to start with for question A, is 56.23 grams. And remember, we want to keep track of what it actually is. So it's grams of Mn2O3. So that's our first piece there. And then our goal is to get to moles. We want moles, and we want moles of manganese, of Mn. Now, I'm going to pull up a second piece of paper just as a reminder here. So the flow chart that we kind of had on the notes is a little useful to keep in mind here. So we have moles of substance 1, or moles, I think it used as of A in the example. We can convert only between substances using moles. So if we want to go, in this question, from grams of manganese to oxygen 3, Mn2O3, and we want to get to just moles of manganese, the only way we can change substances, the only way we can swap from talking about manganese 3 oxide to manganese is doing a mole-to-mole ratio. And this is going to use that ratio in the problem, not a ration. We aren't in that big of an apocalypse yet. And then to get to moles, we can either use grams or we can use particles, which again, particles are atoms, molecules, or FUs, formula units. And we can do the same thing over here. We can go from here to grams, or we can go from here to particles. So it's really just where are you starting with what you've got over here. You'll start at one of these 3 positions. And then where are you ending? You'll end at one of these 3 positions. In this case, we have grams of substance A, and we want moles of a new substance, of substance B. So we're going to have to go from grams to moles and then do a mole-to-mole ratio to figure out what we're looking for. So to do a grams of Mn2O3 to moles of Mn2O3, we're going to use our number over here. This is a grams per mole number, so we can do 157.88 grams in 1 mole. And then we can do mole of Mn2O3, or moles, and we can convert it from moles of Mn2O3 to just moles of Mn. Now to do that one, we don't have a direct conversion factor, but we do have the problem. And the problem tells us for every 2 moles of Mn2O3 we use to break down, we'll get 4 moles of Mn. So for every 2 moles of this, we will get 4 moles of this. Grams of Mn2O3 cancel, moles of Mn2O3 cancel. We're left with moles of Mn, which is what we want. If we plug all this into our calculator, you get to the correct number of sig figs, which in this case should be 4 sig figs, because 56.23 has 4 sig figs. You should get 0.7123, and your unit would be moles of Mn. Okay, hopefully that one made some sense. We're going to do the next problem. We're just going to kind of keep going through these. I'll do a brief pause between them if you want to attempt them and watch these videos one at a time to check your work as you go. But otherwise, we're just going to keep on trucking. So question B, I'll click back so you can see it again just in case. Calculate how many grams of manganese 3 oxide must decompose to produce 0.067 moles of oxygen, moles of O2. Now, I am already writing it, and I'm going to go ahead and click over. If you want to do this on your own, would be the time to pause it and work on it all by yourself. But I've already got my 0.067 moles of O2. And to pull back up my little flowchart thing, we have moles of one substance, of our substance A, and we want to turn it into, or we want to figure out grams of a substance B. So we're going to have to do a mole-to-mole ratio and then do a moles to gram conversion. First step then is a moles to mole ratio. So we have to put moles of O2 on the bottom because we have to cancel that out. And if we want to get rid of moles of O2 and we want to turn that into moles of Mn2O3. So moles Mn2O3. And going back to our balanced equation from earlier, 2 Mn2O3s will give us 3 O2s. So that is a 2 to 3 mole ratio. And now that we have them as moles of Mn2O3, we'll put moles of Mn2O3, and we can convert that into grams of Mn2O3, because that's what the question wants. The question says calculate how many grams of manganese 3 oxide you'd get from this many moles. Grams of Mn2O3 we used a second ago, 157.88, and that's per 1 mole. Moles of O2 cancel, moles of Mn2O3 cancel, grams of Mn2O3 is what you'd be left with. Plugging in that, you should get rounded to the correct number of sig figs. Let me check my work from earlier. I believe this one, 0.067, only has 2 sig figs, so your answer would actually be 7.1 grams of Mn2O3. I think your number you actually get is like 7.05197, but 0.55 would round you up, so it'd be 7.1. Okay, let's click on back for question 3. You can see how these kind of go really quickly. Obviously, I'm also doing it quicker than I assume you guys are because I've just had a lot of practice. Stoichiometry is used in basically every type of chemistry. So don't feel bad if you're like, man, he's making this look so easy. It is also literally my job. Okay, so now for question C. Question C. When 4.90 moles of oxygen are made, how many moles of manganese are also made? So we go back to our hand cam. 4.90 moles of oxygen is what we're going to start with. And this time it just says we want to go from moles of oxygen to moles of manganese. Well, this one is only a one-step problem. We've got to go from moles of substance A to moles of substance B. All we have to do is a mole-to-mole ratio. To convert this second piece of the question, we only have to do a mole-to-mole ratio. So moles of O2 to moles of manganese looks like what we're going to be probably doing. So moles of O2, and it wants moles of manganese, of Mn. And looking back at our question, 4 moles of manganese are made for every 3 moles of oxygen that is made. Moles of O2 cancel. Moles of manganese is what is left. Plugging this into an answer that gives you a 3 sig figs, you should get 6.53 moles of manganese. All right, back to the questions. That one's like the easiest possible ones that you will ever get. Will be ones that are just converting from moles to moles, because then all you really should have to do is a mole-to-mole ratio, at least at this point. I apologize for that cough. Okay, question D. How many grams of manganese are produced when 7.242 moles of manganese 3 oxide reacts? All right, got my problem set up. Let's switch back to hand cam. 7.242 moles of Mn2O3. And we want to go from moles of substance A, and we want to figure out how many grams of substance B. So we're going to need to do a mole to mole and then a mole to gram conversion. So first we'll need moles of Mn2O3 to moles of Mn. And this time I'm not going to write my numbers yet. I'm going to actually just power on through. And this is one of the ways that some people like to do it, because it helps them make sure they've set it up correctly before they start looking up numbers. If we then convert from moles of Mn, we can get grams of Mn. This would allow my moles to cancel here, my moles to cancel here. I'd be left with grams of manganese, which is what I want. So that's a sign that I've done my problem correctly, and I should go back in and fill in my numbers. So that's just another way or approach you can take for these questions. I personally like with these, like filling them in as I go, just so I don't forget to accidentally do something later on. 4 moles of manganese per every 2 of manganese 3 oxide, and then our grams of manganese is 54.94 grams per every 1 mole. Notice that the only things that ever end up with numbers other than 1 with moles is in the mole to mole ratio. Every other time, we haven't done any that involve particles, but particles would be the same way. It's 1 mole per 6.02 times 10 to the 23rd particles. And these are this many grams per 1 mole. The only time you should ever have a number with moles is if the question tells it to you or you're doing a mole to mole ratio. Every other time, your moles numbers should be 1. One of the big mistakes a lot of people make is they'll go, oh, well, in my question, there was 1 moles, or there was 2 moles of this, so I'm going to put a 2 here. But no, that's not what this number is. This number from the periodic table is telling you every 1 mole of substance has this mass. This ratio, a completely separate conversion factor, is telling you that for every 2 manganese 3 oxides you have, you'll get 3 oxygens. Or, that works for all of these problems. But let's go ahead and plug this one in. For grams of manganese with 7.242, you get 795.8 grams, which is a whole lot, but that is a pretty big amount of moles. So it kind of makes sense, especially since some of this stuff is pretty heavy, that you get a decent amount of grams. And again, remember, a gram is like the size of a paper clip. So like 800 paper clips doesn't really actually weigh that much. So yeah, that number makes sense. That number is reasonable. All right, finally, we saved the best for last. Question E. Question E is the longest type of question up to this point that we will have talked about. You want to know how many grams of manganese are formed when 113.95 grams of manganese 3 oxide decomposes. Now, this means, if I flip back to my hand cam, that we're going to have to do a grams to moles, a mole to mole, and then a mole to grams conversion. We're going to have to do 1, 2, 3 whole conversion steps in this problem. And there is going to be some that we'll do that will be a little bit longer than that, but this is going to be the longest type of question currently that you will really be needing to worry about. So first thing we need to do, we don't want Mn2O3 as our answer. We want manganese. So we're going to have to get this closer to manganese, and the only way we can do that is if we convert it to moles, because the only way to change this piece, the only way to change what compound or element you're actually talking about is to convert it into moles and do a mole to mole ratio. So first we're going to have to go grams of Mn2O3 to moles of Mn2O3, which is just our molar mass from the periodic table. So that's our 157.88 per 1 mole. Remember, for this number, you don't look in the problem. Only for our next section, our mole to mole ratio, moles of Mn2O3, and we want to get to moles of just manganese, not Mn2O3. That one we can look in the question. So there's 4 Mn for every 2 Mn2O3. And then for our last section, we can now convert moles of Mn to grams of Mn. So grams of Mn, looking back up here, is 54.94 for every 1 mole. I do want to point out, you can see one of the examples of why it could be a waste of time to calculate some of this. We never used this molar mass of oxygen. I had it in case I needed it, and oxygen's one that you could possibly do in your head, so it's not a huge deal. But if this would have been just like one stage of these questions, like just this question, you would have only needed this number. It would have not really been worth your time to go ahead and figure out every one of these numbers. But on the worksheet where you have like a list of a bunch of things to like work out related to the same question, it might be useful to go ahead and do this, just so you have access to it and you don't end up like having to go back and do it later. Okay, grams of Mn2O3 cancel and have been converted to moles. Moles allow us to do a mole to mole ratio to go from Mn2O3 to manganese, and then moles of manganese cancel, giving us grams of manganese. Now for answering this question, 113.95, that is 5, give a thumb in there, 5 sig figs. So we're going to need to do 79.306, I believe, grams of Mn. I also forgot my label on this one up here, 795.8. It's also grams of Mn. Okay, this question did not have anything like it, but I'm going to switch over to the desktop, and I'm going to answer one of the most common questions that I've gotten related to this. I don't think I answered at the beginning of the video, and if I did, I'm going to answer it again because it's a pretty big deal, and a lot of people were confused about it. So for number 4 right here, let's look at 4A. How many grams of calcium chloride are formed when 76.05 grams of calcium oxide reacts with an excess amount of iron 3 chloride. Excess just means a lot or extra. And what it's basically telling you when it says something is excess in a reaction is that the excess thing you do not need to worry about. It is not going to we will call next week limit the reaction. Think of it like when you're burning a fire. You're not going to run out of oxygen. You're going to run out of firewood first. If you somehow had a fire that burned enough that it used up all of the oxygen in the atmosphere, like, I guess congratulations, you just killed the human species. I don't know where you got that much firewood, but I don't think it's a thing that could really happen unless you're going to other planets and stealing their firewood. So excess just means, hey, this thing's not actually, you don't have to worry about it in your calculation. Just focus on these two numbers. So anytime you see excess amount of something, you literally can just ignore it. You can just we can just pretend it doesn't exist. We can say how many grams of calcium chloride are formed when 76.05 grams of calcium oxide reacts. We can get rid of that too, because that makes the grammar make sense. There you go. You can just pretend that sentence doesn't exist. It's just there to tell you don't have to worry about it. But as I was also a high schooler once, I know that makes you think that you need to worry about it, but no, you don't. Excess is just something that you can discount whenever you're doing your calculation. I hope that was helpful. If you have any questions, email me, leave them in the box to the right. I will probably be doing another update video on Monday just to talk about a couple of things. There'll be a survey probably for what time we're feeling we want to do Zooms. I think I am going to probably do at least once weekly, a non-required Zoom for people to just meet up and ask questions and hang out. And then there'll also be a couple of other things about making sure people know how to submit links. Remember, you can't just copy and paste your URL when you turn in this stoichiometry practice worksheet. You will actually need to go to this file and share button and get a shareable link to be able to share it with me. I hope everybody has a great rest of your day. I hope to see/hear from you soon, and also have a great weekend, everybody.